So mass in minus mass out become accumulation. This is the first equation that we need to use to derive the process model, right? Mass in, what is the if I have a flow rate, right, I multiply by density, this will give me the mass in. If I has the outlet multiplied by the density, this give me the mass outlet. Okay. Accumulation is the volume of the tank change with respect to time. Volume is A multiplied H. Right? When volume multiplied by density, this gives me the change of the mass inside the tank. And ddt means accumulation. And I know that density for all these are constant, which I can cancel that out. So that left me Q in minus Q out equal to A times this. This equation itself already show us how to link the flow rate, the flow rate of the incoming with related to the change of the water level in the tank. Okay, so until equation 2, we sort of like derive the first relationship. Okay, but because I don't want to have Q here and Q not here, I have two unknowns. So if I could replace this Q naught with something related to Q, right, then it will help me, or related to H, then it will help me to take out the Q naught, right? So if we understand earlier that Q outlet here, right, is also equal to H divided by R. This one is given in the question, right? So if I sub this in, I can eliminate another unknown here. So I link the Q incoming to the water level equal to area multiplied the changes of the level in the tank. Okay? Right? So if you look at equation 3, right, this is sort of like a differential equation that I can integrate, then I can link the water level and the incoming flow rate, right? Okay? So by having this equation 3, this is quite good enough as a process model. But if I can improve it more by comparing it to a steady state condition, then I need to introduce a steady state condition. So let's say incoming and outcoming become same. The water level tank will stable at one level, right? And that is the steady state condition. So if I introduce a steady state condition, I know that there will be no change in my water level tank in the tank where in and out is the same. So dH dt becomes 0. So by having that, I said Qs, and this sub S here, right, refer to steady states. So incoming during the steady state minus the water level tank during the steady state divided by this flow resistance equal to 0. The entire purpose here is just I want to introduce another steady state. Okay? So now step 3 is I introduce this deviations variable. Remember our equation 3, right? Equation 3 from the previous one, we have this Qt. And equation 4, we have this steady state. If I use the Qt minus steady state and I rearrange, right, I will have 1 over R. The tank level during the normal time minus the steady state equal to my A. This one is still the same. And then the tank level at any time minus the tank during the steady state. Alright? The entire equation here is just between equation 4 minus equation 3. Right? And I don't want to have so many different unknown here in my equation. If I can replace this one with another symbol, which I call it Q prime. The little dot on the top there, right? Normally we call it a prime. So Q prime is actually the incoming minus the steady state incoming. Alright? So I replace the entire, this one become Q prime. And then the H, the water level, minus the water level during the steady state, I call it H prime. So h prime equal to h minus h during the steady state. So I can replace here and replace here. So equation 5 will be simplified into this equation 6. Q prime equal to 1R h prime plus area multiplied the time change, the accumulations h prime dt. Alright? So if you look at this equation itself, right, it's also a process model equation. It's just that this process model equation now has a different meaning because it's compared to a steady state condition, right? If you compare to equation 3, right, that one is just a normal process process equation. But if you look at a prime here, right, it's actually a normal process equation compared to a steady state condition. And this all whatever the additionals like Q prime, H prime, and H prime here, right, is to help us to understand later if any changes to my system, I compare to a steady state, I know what will be the changes to my output, okay? So just take this equation 6 as your final differential equation, right? Whenever you have final differential equation, the next step what you need to do is to solve it. And I mentioned earlier you can solve it by normal integration, right? Which is very difficult. So we introduce Laplace transform. So which means that over here, I need to transform it. When I transform a small letter, right, if you look at the table, I'll show you the table. Okay. If you look at this table, right, this is a function. This one is a transform. If I transform a function small letter, it becomes capital letter. Same thing apply here. Q prime, if I transform, it becomes capital. Alright? 1 over R is a constant, so you don't change it, you keep as 1 over R. H prime is actually a small capital here. When it transform, become big capital. So H prime transform become capital here. Alright? A is a constant, I keep as it is. And dH prime dt is the differential. If I refer to the table, I should refer to this one and this one. Okay? So if I refer to the differentiation, right? Differentiation after transform is become SF minus small f, right? So this entire thing after transform become S, the small h become big H, right? Minus small h 0. So you have S h minus small h 0, okay? So from 6 to 7, you just transform using the table. Remember 6 is actually a process model I derived from the mass balance compared to steady state. Then I need to solve it. Before I solve it, I transform, okay? And I know that h prime 0 equal to 0. Why? Because if the steady state condition, right, at 0 time, I also compare to steady state, so it's become 0. So I know this one becomes 0, right? So I can simplify my equation become Q prime S 1R H prime plus A S H. This one 0, take it out. Alright? That simplify me to equation 8 if I rearrange it. Okay? So far, clear? Just quickly go through. Yesterday I showed you step by step how to get H divided by Q equal to R divided by tau S plus 1. Okay? And what is this function called? There is a name for this function, right? Transfer function. The entire things here is called transfer function. So if you look at this one definition here, right? The ratio of Laplace transform of the output to the input is known as transfer function. So this one is what? Output or input? H prime is output, right? The bottom one here is input. So output to input, and in this format, we call it the first order transfer function, right? So the system with a transfer function such as equation A are also known as first order system. First orders are quite common in chemical engineering. Why we call this first order is because we only have one the linear equation. You will see second order or higher order if you have more similar sort of transfer function later, okay? So in conclusion is, please remember output divided by input, and in this arrangement we call it transfer function. There's another important thing is this little t here, which we call it tau. Tau is TAU. So this symbol is called tau. And tau in this case has a definition of area multiplied the flow resistance. Okay, we just don't want to put AR. They want you to convert it into this tau, and tau, the name is called time constant. Alright? So if I in future ask you to calculate the time constant, you must know that you need to calculate A multiply R. Okay? And A is the area, R is actually the flow resistance. Okay? I think very quick recap what we learned yesterday. Okay? So the first part of yesterday or whatever we learned is actually the process modeling, normal by mass balance, and we compare to a steady state. After we compare to a steady state, we transform it because we want to solve it. And during the transform, we change it to this transfer function, and we call it first order because it's a linear transfer function. Can? Let's move on. Alright, so it is quite important for us to give some example or put in some value to see how's the changes to this transfer function, right? What we have here, before we move on, let me write it down here. So H prime divided by Q prime S equal to R divided by tau S plus 1. This one is output. Okay, this one is input. Okay, so the ratio or the difference between the output to input is equal to R divided by tau S plus 1. We call it a transfer function. So if the inlet of the flow of the system experience a step disturbance, what does it mean? It means that the inlet now change. And for example, at time equal to 0, the flow rate increase from 10 meter cube per hour to 20 meter cube per hour. What will happen to our output? And output is referred to what? H, right? So if we wanted to calculate and see what will be the changes, this is how we do it. We know that the Q prime at T. Q prime is what? Q prime is the inlet, right? As compared to the steady state, which is at 0. And the question is actually give us that originally is actually at 10, right? And then it's increased to 20, the flow rate. So the level in the tank definitely will change, right? How does the level change? And in terms of the flow rate, inlet is 20 after you compare to the original 10, right? Original 10 is the steady state. So we have a 20 meter cube per hour minus 10 meter cube per hour, okay? This gives us 20 minus 10 is 10, right? Meter cube per hour. So we wanted to know that if the inlet changed from 10 to 20, what will happen to my tank level? And we know that inlet is represented by Q prime, right? And Q prime is equal to 10 here, alright? In order for me to use the transfer function is in the Laplace condition, right? So I cannot use directly this q prime. I must transform it before I can use a transfer function. So to transform q prime, right? This become big Q S, correct? You use the table, Q small capital will change it to big one, right? 10 is actually a unit, right? 1 unit if I transform become 1 over S. 10 if I transform become 10 over S. Okay? This is what we have the equation 9 over there, alright? So if I transform my inlet based on the changes that I have Q prime equal to 10 divided by S, okay? And remember this transfer function that I have here, capital Q prime S now is 10 over S. I can sub inside here. So if I sub in, I get H prime S equal to 10 divided by S multiplied by my R divided by tau S plus 1. Okay? Originally I have this divide QS, right? I move it over here and I know QS is 10 divided S. So this output now is equal to 10 divided S R divided tau S plus 1. Okay? Any questions so far? No, right? Okay, Okay, so the next things now we need to do is we already has the transform format of my output when I put in my input, right? So H prime equal to 10S R tau S plus 1. Now I need to do a inverse for this one. When every time I do the inverse, I must always refer to the table. So for this format itself, which one of the table are the nearest? If you look at the table here, this format, right, over here, right, is nearer to this one, right? Because 1 over S, you can have the 10 over S, right? So the 10 is just a number, so you have 1 over S, tau S plus 1. R and 10 is actually a constant, so R and 10 you can take it out. So you will have 1 over S multiplied 1 over tau S plus 1, which is this one, right? So when I transform, it becomes 1 minus E minus T divided by tau, right? So I should get this, but my 10R is actually a constant that I multiply to it. So if I do that, right, as I said, now I do the inverse, right? When I do the inverse, H capital become small capital, prime is always there, and S become T, right? You always have to bring it back to T. And I said 10R is actually a constant. What I have here is 1S tau S plus 1, right? And this one is actually in this format, 1 over S tau S plus 1, okay? And that, if I transform, is actually 1 minus E minus T over tau. So this entire thing itself, after its inverse, right, it should be, this one after I inverse, right, it should be 1 minus E minus T divided by tau, okay? This is how I got the last one here. From here, inverse become here, 10R is here. 1S divided by this become 1 minus here. Okay? And this is what we have over here. Alright? Never mind, for those has slightly problems to follow, we can discuss later during the consultation. But let me proceed now. Based on this final function we have here, right? We actually complete the entire process. What does it mean here? Which means that my water level change equal to 10 times R1 minus exponential of time divided by area multiplied R. Tau is area multiplied R. Okay? In another word, if I know the time, right, I know the area and resistance, I will know the water tank level after a certain time. Okay? And that is only happen when my incoming change from 20 to 10. If my incoming change to another types of disturbance, this transfer function will also change. Alright? So, in order for you to do this, you always remember your transfer function and you calculate your output based on whatever input that you have. So always back to this equation. You may not need to every time derive this transfer function. You can use it directly. If I tell you this is a first order transfer function, you can always know that output divided by input equal to this. So I only need to tell you if the input disturbance change from what to what, you calculate your Q, and you know R and tau is given, then you can calculate the final relationship between the H and the time. Okay? Okay? So far? Right. Let's move on. Okay? So you can see the transfer function has actually quite numbers of important property of the transfer function and time constant. What is time constant? Time constant is the tau, right? The AR. So transfer function and time constant has some property. There are three important properties that you all need to remember. Let's go through this. Remember if let's say the first order transfer function, we always has y divided by x equal to k divided by tau s. If you compare to the one that I have earlier, this one is h, this one is q, right? This one is r, right? If I don't want to use h, q, and r, because h, q, and r is referred to the water level and also the incoming. But this transfer function can be used for chemical mixing or any other purpose. So I change it to y divided by x equal to k divided by tau s plus 1. So y is output, x is input, k is what? K is what we call it steady state gain. Alright, we'll go through this one later. So a more generic way of the first order transfer is output divided by input equal to k tau s plus 1. Okay? The transfer functions has the first property is allow us to calculate the steady state gain of the process direct in response to a disturbance. Remember, disturbance is always the change in the inlet. Steady state gain of a process is the change of the output variables per unit change of the input at steady state. Alright, let me finish and read out all the things and I go describe to you or explain to you later. This can be done directly at the steady state t equal to infinity or s equal to 1. Setting s equal to 1, equation becomes steady state gain of the system as k. Very long and confusing, right? Alright, an easier way to understand this is steady state gain, right, is the output variable per unit change. Unit change means this one is 1, okay? Output, input, and during the steady state condition, s equal to 0. When s equal to 0, 0 plus 1 is 1. K divided by 1 is k. Alright? So what is steady state gain k here is when the output to the ratio of 1, then you will get k. Alright? It means that anything compared to steady state, the gain will be k. Alright? Just take as this is the first property of the steady state condition. Okay? As I said, property of the transfer function, this is 1. What is the second property of it? Alright? This one you just need to take away is K refer to steady state gain. Alright? Steady state gain based on this definition. Okay? Output, input, and K is steady state gain. So in exam I ask you to calculate steady state gain, right? Remember I asked you to calculate this K. The second property is what? Property means the characteristics of this transfer function. The first characteristic is it has a K as a steady state gain. The second one is for non-interacting process in series, like a process in series, transfer function exhibit a multiplicative property. What does it mean? For example, suppose we have two processes in series with the transfer function G1 and G2. The input to G1 yields an output of X2, and which is to the input of G2. The output G2 is X3. Wow, very long. If you look at this one, right, transfer function means output to the input, right? If I draw this is input, this is output. Transfer function is output to input. So output to input equal to the first transfer function. Okay? The second one, output to input equal to transfer function. So X3 divided by X2 input become the transfer functions of G2, right? If I want to calculate from X3 to X1, where it has two transfer functions in between, right? X3 to X1, I actually can just multiply G1 to G2, alright? This means what? This means that if a series of transfer functions, which is non-interactive, if I want to calculate the last one to the first one, I just need to multiply the two transfer functions. Okay? So this property is very important. Once we know this property, right? If I have a series of reactions, I don't need to derive each of the reactions individually. I know it and I can multiply it together. That will give me the output of the last one to the output to the input of the first one, and I know what is the value. Okay? Give you an example. This second problem, can you understand this one? No understand. It's not easy to understand process control. I can understand that. I can understand that. But somehow you all still need to try. If you write from the beginning, try to derive the thing yourself. You can see the trend. Okay. So the second property or second characteristic is saying that if I have two systems in series and I have one transfer function and second transfer function, I just need to multiply it. I don't need to plus it, I multiply it, which is this one. G1 multiplies G2. Alright? And you have more confusing when you come to the... What? My password lah. You can always read it, it's not a problem. Okay.
Because you always do it.
Right, this one. Alright, let's do it. Incoming is what? Q. And the water level is, let's say H1 for the tank 1, right? We have A1, which is the area of the tank 1. R1 is the resistance of R1. Okay? What we have come out here is Q1. Okay? And this tank flow, the outlet of this tank flow to another tank. Right? In second tank, we have H2. Right? Over here, area also different, R also different. And the outlet here is Q2. Alright? So if you look at this one, it's actually two systems. First system and second system. If I derive the first tank, right, this one is my tank 1. This one is my tank 2, right? If I derive tank 1 and tank 2, right, if I want to link Q2 to the Q1 or H2 to Q1, right, I don't need to individually do it again. I can, if I know the transfer function, I can just multiply the transfer function in order for me to guess what are the changes to the, let's say, H2 when the incoming change. Alright? This is what we mean. Let's do it one by one here. Okay? And we know for the first tank, let's say for this first tank itself, what is the transfer function we have? Transfer function for for tank 1, right? Tank 1. Right? We have H1 prime when transfer function is what? Output to the input, right? Output is the height of this tank level. What is the input to the tank 1? Q, right? Q has to change it in the transfer function is in the Laplace format, right? So it has to be Q prime S, alright? And R1 is for tank 1, okay? And tau 1, of course, is A1 times R1. This one is tau, right? So I got tau 1, right? S plus 1. This one is for tank 1, okay? What about tank 2? Similar condition. Tank 2. Tank 2 is between the H2 and Q1, right? So your output is H2, right? So you have H2 prime S. What about your input? Input is Q1, right? So you have Q1. You have Q1 prime S, okay? And your tank 2, the resistance is R2, right? Divide by, this one is, this 2 multiplied is tau 2, right? So I got tau 2 S plus 1. This one is my tank 2, right? So I have transfer function for tank 1, I have transfer function for tank 2, right? Basically, if I multiply these two, I know the series. If I want to link, let's say, H2 to H1, I can just multiply these two functions. Okay? So far, alright? Okay, let's move on. But before I use this one, right, there are too many. I got H1, Q1, H2, Q2. Can I eliminate the Q1? I actually can eliminate the Q1 by introducing this outflow. Okay? Let me read out this one. We have also know that the outflow rate is related to the height. So Q1, remember Q1, right, is also equal to H1 divided by R. Correct? This Q1 is equal to H1 divided by R, right? So Q1 equal to H1 divided by R. At steady state, my Q1 steady state equal to H1 steady state divided by R1, right? Okay? And I introduce this deviation variable, which is Q1 prime, right? Q1 prime. And Q1 prime at T equal to Q1 prime T minus QS. Alright? And H prime 1T equal to H1T, sorry, H1, this one is 1T minus HS. The entire purpose here is I wanted to eliminate Q1 here. So I introduce this. Confused? Okay. Before I move on to this one. This tank 1 and tank 2, the transfer function, you're okay, right? assume okay. Okay, assume you're okay. So this one I have H1, I have Q, which means I have H1 and Q. Alright? And the other one I got H2 and Q1. If I wanted to replace this Q1, how? Because I don't want to have too many Q. I got H1Q, H2, Q1. If I wanted to eliminate this one, I go back to the original Q1 here. I know that this Q1 that's in between of it, right, is actually the transfer, is actually the H divided by R. So I got this Q1 equal to H1 divided by R1. I introduce a variable here, and that's give me this equation, which is Q1 prime at T equal to H1 prime at T divided by R1. Okay? So let me move on and I'll summarize later. So after this part, I transform. I need to transform this one. When I transform this one, I got Q1 prime S equal to H1 prime S divided by R1. Okay? This equation itself, if I wanted to get, let's say, okay, let's say, now Q1 here, right? Can I replace this Q1? Can, right? So if I replace this one inside this equation, I have H2 divided by, okay, let me do it this way. If I want to have H2 prime S divided by Q prime S, this equal to H2 prime S divided by Q1 prime S multiply Q1 prime S divided by R1. Okay? No, not R1, H1, sorry. Divided by H1 prime S multiplied by H1 prime S divided by Q prime S. H2 to Q1. H2 to Q1 is, let me see. Okay. H2 is which one? H2 is this one. To Q1. Q1 is this one, right? H2, is it Q1? Q. Oh, sorry.
I say this is so me when I teach P5 math.
You don't know what's
Okay.
Yeah, I'm like, why do you test this?
If you look at this one, right? HQ to Q, right? HQ to Q, right? Over here, H2 to Q. H2 is the last one to the first one, right? Is equal to the transfer functions, the first one, which is H2 to Q1 multiplied by Q1 to H1 multiplied by H1 to Q1, right? Can you see the link for this tree? I have three transfer functions here. When I have two systems in series, right? I want to link the level here to the Q1 the Q input here. How should I do? I use this transfer function. This one is the output to the input, right? Multiply to output to the input. Multiply to output to the input. This is what I have here. H2 is the output of the second one to Q1, right? And Q1 to H1 is output to the input of the middle one, right? The first one is H1 to Q. Can you see that? I have this output. If I want to calculate this output to this input, which is H2 to the input, which is Q, right? So H2 to the first one is actually H2 to Q1. So H2 to Q1, alright, is the first one. And then after that, between the Q1 and H1, I have Q1 and H1, alright? Followed by H1 to Q, then H1 to Q. Okay?
Yes, sir.
Okay?
Goyang sih gambar tu.
The whatever we have here, right, is to link between
Bangun dia goyang.
all the three items here.
Dia ni.
If I have the tank 1, H1 is my output to my Q. Tank 1, the output is H1, right? Q is my input. And this is my function, alright? I leave the function as it is. Tank 2 is, H2 is my input, right? H2 is my output, Q1 is my input, and this is my transfer function, right? And then in between, right, Q1 and H1 can link by this equation. So whatever I derive here is just for me to get this Q1 prime linked to H1 and R1. So in between of Q1 and H1 is the second part where I derive, okay? So if I go back to, I want to link H2 to Q, I use this transfer function, output to input, multiply output to input, multiply output to input, okay? And that's give me the final one. H2 to Q equal to first, second, third, alright? Now, H2 to Q1, right? H2 to Q1 is actually H2 to Q1, which is this transfer function, right? Can I replace this one in? So this becomes my R2 divided by tau 2s plus 1, okay? Q1 to H1, Q1 to H1 is which transfer function I have? Q1 to H1 is 1 over R1, right? Q1 to H1 is 1 over R1. So this one is 1 over R1, okay? The third one, H1 to Q1, is actually H1 to Q is this transfer function, right? So the third one, I put in the R1 divided by tau 1s plus 1, okay? And this actually can help me cancel out this. So what left is R2 divided by tau s plus 1. Actually it's tau 2s plus 1 multiply tau 1s plus 1. Okay? H2 prime s divided by Q prime s. Wow. Right. In short, right, along the step to derive the whole thing, just to tell you the level in the tank 2 with respect to the input from the floor equal to the flow resistance of 2 divided by this plus multiplied by this and multiplied by this, and this gives us flow of 2, well, level of 2 divided by flow equal to resistance 2 tau s plus 1 tau s2 plus 1, okay? So if you have two tanks linked together, the second tank water level height is linked to the input plus R2 and this time constant. R1 is not need to calculate, alright? In summary, this is the form that we have. Remember tank 1, the output is H1 linked to Q, right? Between the Q1 and H1, you have this transfer function. Between the level in tank 2 to Q1, you have this transfer function. So you use this, multiply this, will give you to link between the second one to the first one, right? Okay? So this is what we call the second property. If you have non-interacting system, the transfer function is multiply the second one to the first one in order for you to link the last output to the first input. Alright? Yes, another important thing is the third property. I need to finish these three properties before we go for consultations or what. The time constant is indicative of the speed of the response of the process. Remember what is time constant? The tau, right? A times R. This A times R, the time constant, has a property that the smaller tau means that the response is faster. So if my tau is small, then the response is faster. The big tau means the response is sluggy or slower. And this can be represented by this format. So you can see that smaller r, the response is faster. So let's say at any time, right, the height change faster because the slope here is higher than slope here and higher than slope here. This is just for your info only. You just need to remember the time constant tau increase, the process becomes sluggy, right? I will not go through this one. We'll go through this one next week. All right? Can my God. So what you need to take away from today's lesson is there are three important properties of the transfer function. First one is what is K, the steady state gain, right? That's derived from the first transfer function. Second one is if I have two systems integrated, non-interactive, I need to calculate the third output to the first one. I just multiply the two transfer functions together. The third one is this time constant. If the smaller the time constant, the faster the system is. Alright, so sometimes we may just give you the time constant and ask you to tell which one has a faster process dynamic. Alright? Okay, I think that's all for today. I'll stay back here and I will go through one by one if you want, or anyhow, let me know your problems, we can discuss. I don't want you all to proceed later with a lot of confusion because moving on, right, those slides behind is even more confusing, alright? Thank you. And those who need to meet your lecturer, please proceed to level 5. Yes. Lecture quiz. I cannot remember the time. I don't think we have lecture quiz. We only have term test 1, term test 2, not term test 2, term test 1 and final, and your practical. Yes, if I remember correctly, please refer to the teaching plan.